Hello everyone, in this lecture, I'm going to show to you how to derive the mean, the variance, and the moment generating function for the double exponential distribution. Double exponential distribution is a continuous probability distribution with a probability density function or PDF shown in here. Now let us start with our derivation of mean. Mean is equal to expectation of x. Since this is a continuous probability distribution, it is equal to the integral of x times the probability density function, which is this one here, then dx. This x is from negative infinity to positive infinity, so we have here negative infinity to positive infinity. Then let us move this constant outside of this integral, so we have this one from here. Then in order to evaluate this integral expression, we need to find a way to remove this absolute value sign. Now from the definition of the absolute value of x minus mu is equal to positive x minus mu if this x minus mu is positive, that is, it is greater than or equal to 0. Then moving this mu to the right side, we have x is greater than or equal to mu. This absolute value of x minus mu is equal to negative of x minus mu if this x minus mu is less than or equal to 0. Then moving this mu to the right side, we have x is less than or equal to mu. Now, based from the idea in here, we can divide this integral expression into two. One in which x is from negative infinity to mu, which is this one, from negative infinity to mu, and the other one in which x is from mu to positive infinity, which is this one, from mu to positive infinity. Then in here, x is always less than or equal to mu, since x starts from negative infinity to mu. Then we are in here. Then the absolute value of x minus mu is negative of x minus mu. Then using this one in place of this one in here, we have negative of x minus mu or positive x minus mu, which is this one. Then for this one, x is greater than or equal to mu, since x starts from mu to positive infinity. Then we are in here. Then the absolute value of x minus mu is just x minus mu. Then using this one in place of this one in here, we have negative of x minus mu, which is this one. Then observe that we have removed already the absolute value sign from here. Then we're ready to evaluate each integral expression. Now let us first evaluate this integral expression in here. We can use the integration by parts, which is integral of u dv is equal to uv minus integral of v du. Let this u to be x, which is this one. Then dv will be the rest of the terms, which is e raised to x minus mu over sigma dx. Then du will be the derivative of x, which is dx, and v will be the integral of this one. Now to integrate this one, we have a formula from calculus, that is integral of e raised to y dy is equal to e raised to y. If we let y to be the exponent x minus mu over sigma, which is this one, then dy will be the derivative of this one, which is 1 over sigma dx. Then in here, we have e raised to y, which is this one, but for dy we don't have this 1 over sigma in here. Then since this is a constant, what we're gonna do is to multiply this one by this 1 over sigma, but also the reciprocal of this one, which is sigma, in order not to change its value. Then we have here the reciprocal of 1 over sigma, then times this one, e raised to y, which is this one. Then for the integral of u dv, which is integral of this one, I have rewrite it in here, is equal to uv, which is x times this one, which is this one, to be evaluated from negative infinity to mu. Then minus integral of v du, v is this one, in here, then du will be dx, which is this one. Then we can put the sigma to the left side, so we have this one sigma in here, and also the sigma outside of this integral, so we have this one from here. Then let us substitute this mu for x in here. We have mu minus mu, which is 0, then 0 divided by a constant, which is greater than 0, still 0. And then e raised to 0 is 1, so we have here 1. Then if we substitute again this mu for x in here, we have here sigma times mu times 1, which is sigma mu. So we have here sigma mu. Then minus, if we substitute this negative infinity for x in here, we have negative infinity minus constant is still negative infinity, and negative infinity divided by constant which is greater than 0 is still negative infinity. So we have here e raised to negative infinity, or this one equal to 1 over e raised to infinity, or equal to 1 over infinity since e raised to infinity is still infinity. And 1 over infinity is equal to 0, then we will have here 0 for e raised to this term. So let me write it in here 0, then times this term. Now if we substitute this negative infinity for x in here, we have here sigma times negative infinity is still negative infinity, so we have here negative infinity. Now for this 0 times negative infinity, we don't know if this is 0 or negative infinity. So what we're gonna do to determine the value of this one, we need to use the L'Hospital's rule. In L'Hospital's rule, the limit of f of x over g of x as x approaches a is equal to limit of the derivative of f of x with respect to x over the derivative of g of x with respect to x as x approaches a. Then using this one in here, we can rewrite this one, excluding the constant sigma, to be x over the reciprocal of this one, which is e raised to negative of x minus mu over sigma. Then we have here as x approaches negative infinity. Then using this L'Hospital's rule, we have limit of the derivative of x is 1, and for the derivative of this one, for the exponent we have negative 1 over sigma, which is this one. Then we have e raised to this one, which is this one. Then substituting this negative infinity for x in here, we have negative infinity minus constant is still negative infinity, and negative infinity divided by constant which is greater than 0 is still negative infinity. And negative of negative infinity is positive infinity, so we have here e raised to positive infinity, which is this one. Then this e raised to positive infinity is still positive infinity, and multiplying this one by negative 1 over a constant which is greater than 0 is negative infinity, so we have here negative infinity. Then 1 over negative infinity is 0. So we have here 0 instead of 0 times negative infinity because of this one. Then we are in here sigma mu minus 0. Then minus, for the integral of this one, we have evaluated it already. This e raised to x minus mu over sigma dx is same with this one over dv. Then the integral of this one is this one sigma times e raised to x minus mu over sigma, and then using this one in place of this one, we'll get sigma squared times e raised to x minus mu over sigma, which is sigma times this one. Then it has to be evaluated from negative infinity to mu. Then we have here sigma squared, which is a constant, and then substituting this mu for x in here, we have mu minus mu, which is 0, and 0 divided by constant which is greater than 0 still 0, and e raised to 0 is 1, so we have here 1. And then substituting this negative infinity for x in here, we have negative infinity minus constant is still negative infinity, and negative infinity divided by constant which is greater than 0 still negative infinity. And e raised to negative infinity is 0, so we have here 0. Then simplifying it, we'll get sigma mu minus sigma squared times 1, which is sigma squared. So we have now our result for evaluating the first integral expression. Now for the second integral expression, which is this one, we're gonna do the same with what we have done in the first integral expression. Let us use again this integration by parts. Let u be x, and dv will be the rest of the terms, which is e raised to negative of x minus mu over sigma dx, which is this one. Then du will be the derivative of this one, which is dx, and v will be the integral of this one. To integrate this one, let us use this formula from calculus. Let y be the exponent of this e, which is negative of x minus mu over sigma. Then dy will be the derivative of this one, which is negative of 1 over sigma. Then we have here dx. Then for this one, we have e raised to y. But for dy, which is this one, we don't have this 1 over sigma. Then what we're gonna do is to multiply this one by negative 1 over sigma, which is just a constant. And also we need to multiply it by the reciprocal of this one, which is negative sigma, in order not to change its value when we multiplied it by negative 1 over sigma. then we have here the reciprocal of this negative 1 over sigma times e raised to y, which is this one. Then for the integral of u dv, which is same with this one, we have uv, which is x times this one, which is this one. Then it has to be evaluated from mu to positive infinity. So we have here mu to positive infinity. Then minus integral of v du. For v, we have this one, negative sigma e raised to negative x minus mu over sigma. Then du will be dx, which is this one. Then simplifying it, we can move this negative sigma to the left side, which is this one. And then minus of negative is plus. We can move the sigma to the left side, we have here sigma. Then, if we substitute this positive infinity for x in here, we have positive infinity minus constant is still positive infinity, and positive infinity divided by constant, which is greater than 0, still positive infinity. And negative or positive infinity is negative infinity, so we have here e raised to negative infinity. And then e raised to negative infinity is 0, so we have here 0. Then times, if we substitute again this positive infinity for x in here, we have negative of sigma times positive infinity, which is negative infinity. Then we have same dilemma with the first integral expression. Let us use again the L'Hospital's rule. This one, excluding negative sigma, can be rewritten as x over the reciprocal of this one, which is e raised to x minus mu over sigma. Then using the L'Hospital's rule, derivative of x with respect to x is 1. And then for the derivative of this one with respect to x, let us differentiate first the exponent, which is 1 over sigma. Then this one, e raised to x minus mu over sigma. Then we have here, x approaches positive infinity, and also in here. Then substituting this positive infinity for x in here, we have positive infinity minus constant, still positive infinity, and positive infinity divided by constant, which is greater than 0, still positive infinity. So we have here positive infinity. But e raised to positive infinity is still positive infinity, and positive infinity times 1 over a constant which is greater than 0, still positive infinity. And 1 over positive infinity is equal to 0. Then we have here 0. So we have this one 0 when we substitute this positive infinity for x in here and also in here. Then minus, if we substitute this mu for x in here, we have mu minus mu, which is 0, and 0 divided by constant, which is greater than 0, still 0. So we have here negative 0, or just simply 0, and e raised to 0 is 1. So we have here 1 when we substitute this mu for this e raised to this one. Then if we substitute again this mu for x in here, we have negative sigma times mu times 1, which is negative sigma mu. So we have here negative sigma mu. Now for the integral of this one is same with this one. So the integral of this one is just this one, negative sigma e raised to negative x minus mu over sigma. Then using this one in place of this integral expression, we have sigma times this one, which is this one. Then it has to be evaluated from mu to positive infinity, which is this one. Then for this one we have minus of negative, which is positive sigma mu, which is this one. Then we have plus and negative, we have minus sigma times sigma, which is sigma squared. Then substituting this positive infinity for x in here, we have positive infinity minus constant is still positive infinity, and positive infinity divided by constant, which is greater than 0, still positive infinity. And then we have here negative or positive infinity, which is negative infinity. Then e raised to negative infinity is 0. Then we have here 0, which is this one, when we substitute this infinity for x in here. Then minus. Then if we substitute this mu for x in here, we have mu minus mu, which is 0, and 0 divided by constant, which is greater than 0, still 0. And negative 0 is still 0, and e raised to 0 is 1. So we have here 1. Then we have here sigma mu minus and minus, we have plus, then sigma squared times 1, which is sigma squared. Then the result of evaluating this integral expression is sigma mu plus sigma squared. Now for our mean, which is equal to 1 over 2 sigma times sum of our results from evaluating each integral expression, we have here we have here rewritten from above n equal to 1 over 2 sigma times the result from the first, which is this one, sigma mu minus sigma squared, plus the result from the second, which is sigma mu plus sigma squared. Then we can cancel out this minus sigma squared and plus sigma squared, so we're left with sigma mu plus sigma mu, which is 2 sigma mu. Then we can cancel out this sigma and sigma, this 2 and this 2, so we're left with mu, which is this one. And then now we have our mean for the double exponential distribution, which is just mu. Now let us proceed with our derivation of variance. Variance is equal to expectation of square of x minus expectation of x. For expectation of x, it is same with the mean, so we have derived it to be equal to mu. So we can use this mu for expectation of x. Now since this is a continuous probability distribution, this one is equal to the integral of square of x minus mu, which is expectation of x, times the probability density function, which is this one in here. Then dx. This x is from negative infinity to positive infinity, so we have here negative infinity to positive infinity. Then we can move this constant outside of this integral, so we have this one from here. Now for this integral expression, we have to integrate this twice. So in order to simplify our integration process, we can transform this one into a simpler form using the transformation function z is equal to x minus mu over sigma. Then from here, x minus mu is equal to sigma z. Then x will be sigma z plus mu. Then dx will be the derivative of this one, which is sigma dz, since z is the only variable in here. Then substituting this in here, we have our constant from here. Then for x minus mu, we can use this sigma z, which is this one in here. Then for this x minus mu, we can also use this sigma z, which is this one in here. Then for dx, let us use this one, sigma dz, so we have this one from here. Then for our limits, if x is negative infinity, in here we have negative infinity minus constant, still negative infinity, and negative infinity divided by constant, which is greater than 0, still negative infinity. So we have here negative infinity. Now if x is positive infinity, we have here positive infinity minus constant is still positive infinity, and positive infinity divided by constant, which is greater than 0, still positive infinity. So we have here z is positive infinity when x is positive infinity. Then for this one, absolute value of sigma z over sigma, which is rewritten in here. This absolute value of sigma z can be rewritten also as absolute value of sigma times absolute value of z. And then since this sigma is always greater than 0, then we can remove this absolute value sign, since it is always positive anyway. Then we can cancel out the sigma and sigma. So we'll have here with absolute value of z, which we can use for this one. Then from here, we can cancel out the sigma and sigma in here. Then we can move out the sigma raised to 2 outside of this integral, so we have this one from here. Then for this one, absolute value of sigma z over sigma, we can replace it by just absolute value of z, so we have here absolute value of z from here. Then we have here dz. Now similar to what we have done in our derivation of mean, we need to find a way to remove this absolute value sign in here. From the definition of the absolute value sign, the absolute value of z is equal to positive z if z is greater than or equal to 0, and it is negative z if z is less than or equal to 0. Then, using this concept, we can divide this integral expression into two. One in which z is from negative infinity to 0, which is this one, plus this expression in which z is from 0 until positive infinity, which is this one, from 0 to positive infinity. Now in here, z is always less than or equal to 0, since z starts from negative infinity until 0 only. So we are in here. Then the absolute value of z is negative of z, and if we use this one in place of this one in here, we have negative of negative z or positive z, which is this one. Then for this one, z is always greater than or equal to 0, since z starts from 0 until positive infinity. Then we are in here. Then the absolute value of z is equal to positive z. And if we use this one in place of this one in here, we get negative of z, which is this one. Then observe that we have removed already the absolute value sign in here. Then we're ready to evaluate these integral expressions. Now let us evaluate this integral expression first, which is this one. We can use integration by parts to integrate this one. So we have this formula, integral of u dv is equal to uv minus integral of v du. If we let u to be z squared, then dv will be the rest of the terms, which is e raised to z dz, which is this one. Then du will be the derivative of this one, which is 2z dz. And v will be integral of this one, which is just e raised to z. Then using this integration by parts, removing first the limits, which is from negative infinity to 0, we have this one, which is integral of u dv without the limits. Then uv will be this u, z squared, times this v, which is e raised to z. So we have here z squared times e raised to z. Then minus integral of v du. We have here v, which is e raised to z in here. Then du, which is 2z dz. So we have here 2z dz. Then we can move this 2 to the left side and then put this z in front of e raised to z. So we have here z times e raised to z. Then let us evaluate this again, integral of z e raised to z dz, using integration by parts. Now in here, let u be z. Then dv will be the rest of the terms, which is e raised to z dz, which is in here. Then du will be derivative of this one, which is dz. And v will be the integral of this one, which is e raised to z. Then this one, which is integral of u dv, is equal to uv, which is z times e raised to z in here. Then minus integral of v du. We have integral of v, which is e raised to z. Then du is dz in here. Then we have z e raised to z minus the integral of e raised to z dz is just e raised to z. Then we can substitute this one in here. So we'll get, for this one, it is equal to this one, z squared e raised to z. Then minus 2 times this one, which is this one, z e raised to z minus e raised to z. Then distributing this negative 2 for its term in here, we get negative 2 z e raised to z by multiplying this negative 2 and z times e raised to z. And we have here plus 2 e raised to z by multiplying this negative 2 and minus e raised to z. Then we have here a common term, e raised to z. Let us factor this expression by e raised to z. So we have here z squared minus 2z plus 2 times the common term, which is e raised to z. Then let us bring back the limits, which is from negative infinity to 0. So we have here negative infinity to 0, and also this one, it has to be evaluated from negative infinity to 0. Then if we substitute this 0 for z in here and also in here, we get here 0 minus 0, then plus 2. So we're left with 2. So we have here 2. Then if we substitute this 0 for z in here, we have e raised to 0 or 1, so we have here 1. Then minus, if we substitute this negative infinity for z in here, we get positive infinity, and negative of negative infinity is positive infinity, then plus 2 is still positive infinity, so we have here positive infinity. Then if we substitute this negative infinity for z in here, we have e raised to negative infinity, or 1 over e raised to infinity, and this 1 over e raised to infinity is 1 over infinity, since e raised to infinity is infinity, then it is equal to 0. So we have here 0 when we substitute this negative infinity for z in here. Then we have here infinity times 0, which can be infinity or 0. So in order to determine the value of this one, similar to what we have done in our derivation of mean, we need to use the L'Hospital's rule. Again, in L'Hospital's rule, which is this one, which is limit of f of x over g of x as x approaches a, is equal to limit of the derivative of f of x with respect to x over the derivative of g of x with respect to x as x approaches a. Then applying this one in here, this one can be rewritten as this z squared minus 2z plus 2, which is from here, then over the reciprocal of this one, e raised to z, which is e raised to negative z. Then as x approaches negative infinity, which is this one. Then from here, it is equal to the limit of the derivative of this one is 2z minus 2. Then the derivative of this one is negative of e raised to negative z. Then let us again apply this rule in here. We'll get the derivative of 2z minus 2 is just 2. And then the derivative of this one is negative of e raised to negative z, which is just e raised to negative z. Then substituting this negative infinity for z in here, we'll get e raised to negative of negative infinity or positive infinity. So we have here e raised to positive infinity or just positive infinity. Then 2 over positive infinity is 0. So we have here this one should be 0. Then the value of this one is just 2 times 1 or 2. So we have this one, the result for the evaluation of our first integral expression. Then for the second integral expression, which is this one, let us rewrite this one below. So we have this one from above. Then we're gonna use the same approach as we did with our first integral expression. Let us use again the integration by parts. Let u be z squared. Then dv will be the rest of the terms, which is e raised to negative z dz. Then du will be the derivative of this one, which is 2z dz. Then v will be the integral of this one, which is negative of e raised to negative z. Then the integral of u dv, which is this one in here, is equal to uv, which is u, which is z squared over 2, times v, which is negative of e raised to negative z in here. Then minus integral of v du. In here, v is negative e raised to negative z times du, which is 2z dz. Please take note that we ignored temporarily the limits in order to simplify our evaluation. Now from here, we can move this negative to the left side. We have e raised to negative z, and we have here minus and negative, which is plus. Then we can move this constant outside of this integral, so we have these two. Then we can move this z before e raised to negative z, which is this one. Then for this integral of z times e raised to negative z dz, let us again use this integration by parts. We have that u be z, and then dv is the rest of the terms, which is e raised to negative z dz. Then from here, du is equal to derivative of this z, which is dz. Then v will be the integral of this one, which is negative of e raised to negative z. Then this one, integral of z times e raised to negative z dz, which is integral of u dv, in here is equal to uv, which is z times negative of e raised to negative z. So we have this one for uv. Then minus integral of v du. For v, we have this one, negative of e raised to negative z in here. Then du will be this one, dz, which is in here. Then we can put this negative to the left side, which is this one. Then minus and negative is plus. Then for the integral of e raised to negative z dz, we have just negative of e raised to negative z without this dz. Then let us substitute this in here, so we'll get this one in here, then plus 2 times this one, which is this one in here. Then let us distribute this 2 for each term in here. Then we have negative 2 from here. Then we have negative 2 also from here. Then in here, we have a common term, negative of e raised to negative z. By factoring it out by negative of e raised to negative z, we get negative of e raised to negative z times the rest of the terms, which is z squared plus 2z plus 2. Then it has to be evaluated from 0 to positive infinity. So we have this one, 0 to positive infinity, and also in here to be evaluated from 0 to positive infinity. Now if we substitute this positive infinity for z in here, we'll have here e raised to negative infinity or 0. So we have here 0. Then times, if we substitute this positive infinity for z in here, we have positive infinity squared, which is still positive infinity, and then plus 2 times positive infinity, still positive infinity, and positive infinity plus 2 is still positive infinity. So we have here positive infinity. Then we have minus, if we substitute this 0 for z in here, we get negative of 0 or just 0, and e raised to 0 is 1. So we have here negative 1 in here. Then times, if we substitute this 0 again for each term in here, we get 0 plus 0 plus 2, which is just 2. Now for this one, negative 0 times infinity, we don't know if it is just 0 or negative infinity. So in order to evaluate that, we need again to use the L'Hospital's rule. Now using the L'Hospital's rule, this one can be rewritten as z squared plus 2z plus 2, which is this one, over the reciprocal of this one, negative of e raised to negative z, which is negative of e raised to z. Then limit of this one as x approaches positive infinity. Then using the L'Hospital's rule, the derivative of this one is 2z plus 2, which is this one, and the derivative of this one is just same, negative of e raised to z, as x approaches positive infinity from here. Then again, applying the L'Hospital's rule, the derivative of 2z plus 2 is just 2, and the derivative of this one, we have this negative of e raised to z, which is same with this one. Then we have here again, as x approaches positive infinity. And then if we substitute this positive infinity for z in here, we get 2 over e raised to positive infinity is still positive infinity, and negative of positive infinity, we get negative infinity. And 2 over negative infinity is 0, so we have here 0. So what we're left with is minus of negative 1, which is positive 1 times 2 is 2. So the value of this integral expression is just equal to 2. Now let us go back to our formula for our variance. So our variance is just this one. It is equal to this constant sigma squared over 2 times the sum of our results from our evaluation of each integral expression. So we have here variance is equal to sigma squared over 2 times our first result is this 2 for our first integral expression, which is this one, and then for our second integral expression, we have also same, which is 2 in here. Then we have 2 plus 2 is 4, and 4 over 2 is 2, so we have here 2 sigma squared. Then we have here now our variance for the double exponential distribution. Now let us proceed with our derivation of the moment generating function. The moment generating function has the formula expectation of e raised to tx. Since this is a continuous probability distribution, it is equal to the integral of e raised to tx, which is from here, times the probability density function, which is this one in here, then dx. This x is from negative infinity to positive infinity, so we have here negative infinity to positive infinity. Then let us move this constant outside of this integral, so we have this one from here. Now similar to what we have done in our derivation of mean and variance, we need to find a way to remove this absolute value sign. Now from the definition of the absolute value of x minus mu is equal to positive x minus mu if this x minus mu is positive, that is, it is greater than or equal to 0. Now if we move this mu to the right side, we have x is greater than or equal to mu. This absolute value of x minus mu is equal to negative of x minus mu if this x minus mu is less than or equal to 0. Then moving this mu to the right side, we have x is less than or equal to mu. Now similar to what we have done in our derivation of mean, we can divide this integral expression into two. One in which x is from negative infinity to mu, and the other one in which x is from mu to positive infinity. In here, x is always less than or equal to mu, since x starts from negative infinity to mu. So we are in here. Then the absolute value of x minus mu is equal to negative of x minus mu. Then using this one in place of this one in here, we have negative of x minus mu or positive x minus mu, which is this one. Then for this one, x is always greater than or equal to mu, since x starts from mu until positive infinity. Then we are in here. Then the absolute value of x minus mu is just x minus mu. Then using this one in place of this one in here, we have negative of x minus mu, which is this one. Now observe that in these integral expressions, we have removed already the absolute value sign. So we're ready to evaluate them. Now let us combine the exponentials in here. We have e raised to tx plus x minus mu over sigma. In here, doing the same, we have e raised to tx minus x minus mu over sigma. Then let us collect terms with x. For this one, so we have t plus 1 over sigma, x, then minus mu over sigma. And also in here, we have t minus 1 over sigma, then x, then minus and minus is plus mu over sigma. Then let us evaluate this integral expression first. In order to evaluate this integral expression, we can use the formula from calculus, which is integral of e raised to u du is equal to e raised to u. Now if we let u to be this one, the exponent of e, which is copied in here, t plus 1 over sigma x minus mu over sigma, then du will be the derivative of this one. Since x is the only variable in here, we have t plus 1 over sigma dx. Now in here, we have e raised to u, which is this one, e raised to u. Now for the du, which is this one, we don't have this t plus 1 over sigma. Now in order to have this one in here, since this is a constant, we can multiply this one by t plus 1 over sigma, but we need also to multiply this one by the reciprocal of this one, in order not to change its value. Then we have this one, the reciprocal of this one, which is this one, 1 over t plus 1 over sigma, times e raised to u, which is this one, e raised to, this one is our u. Now this one has to be evaluated from negative infinity to mu, so we have here negative infinity to mu. Now let us substitute this mu for x in here, and then distribute it with each term in here, t and 1 over sigma. So we have this one. So we have from here mu t plus mu over sigma, then we have this one minus mu over sigma. Now if we substitute this negative infinity for x in here, if this t plus 1 over sigma is greater than 0, then we will have here negative infinity. And negative infinity minus constant is still negative infinity, and we will have here e raised to negative infinity. E raised to negative infinity is equal to 1 over e raised to infinity is equal to 1 over infinity, since e raised to infinity is still infinity. Then 1 over infinity is equal to 0. So we have here 0 if we take this t plus 1 over sigma to be greater than 0. Now if this one is 0, this t plus 1 over sigma, then this one will also be 0. Then we will have 1 over 0 or infinity. So this one will be infinity and our moment generating function will be infinity. To avoid that our moment generating function to be infinity, we need to ensure that this t plus 1 over sigma is not equal to 0. Then, if this one is negative, this t plus 1 over sigma, then substituting this negative infinity for x in here, we have negative of negative infinity or positive infinity. And positive infinity minus constant is still positive infinity, and e raised to positive infinity is still positive infinity. Then we will have a moment generating function which is infinity. So to avoid that, we need also to ensure that this t plus 1 over sigma is not less than 0. So we have only one condition that makes our moment generating function to be not infinity. That is this one. T plus 1 over sigma should be greater than 0. Then we can cancel out this plus mu over sigma and minus mu over sigma. Now for this one, we have a common denominator sigma if we multiply the numerator and denominator of t by sigma. And then we'll have here sigma t plus 1 over sigma. And 1 over that is sigma over sigma t plus 1. Then we can cancel out the sigma and sigma. Then what we're left with is 1 over 2 sigma t plus 1 e raised to mu t with this condition. If we move this 1 over sigma to the right side, we have t is greater than negative 1 over sigma. Now for the other integral expression, which is this one, let us rewrite this one below, which is this one. Then let us use again this formula from calculus. Then we're gonna do similar approach with what we have done in the first integral expression. Now let u be the exponent of e, which is t minus 1 over sigma x plus mu over sigma, which is this one. Then du will be the derivative of this one, which is t minus 1 over sigma dx. Then in here we have e raised to u, which is same with this one. But for du, we don't have this t minus 1 over sigma. Then similar to the first integral expression, we need to multiply this one by t minus 1 over sigma and its reciprocal in order not to change its value. Then we have here 1 over t minus 1 over sigma times e raised to u, which is e raised to this u, which is same with this one. Then we have here limits mu to positive infinity, so we have here mu to positive infinity. Then let us substitute this infinity for x in here. Now if this t minus 1 over sigma is greater than 0, then we will have here positive infinity, and positive infinity plus a constant is still positive infinity, and e raised to positive infinity is still positive infinity. Then we will have a moment generating function which is infinity. So to avoid that, we need to ensure that this t minus 1 over sigma is not greater than 0. Now if this t minus 1 over sigma is 0, then this one we will have here 0, and 1 over 0 is infinity, and again we have a moment generating function which is infinity. So we need also to ensure that this t minus 1 over sigma is not equal to 0. Then if this t minus 1 over sigma is less than 0, then substituting this infinity for x in here, we have negative infinity, and e raised to negative infinity is 0. Then we will have here an expression which is 0. So we have this one, 0, with the condition that this t minus 1 over sigma is less than 0. Or if we move this 1 over sigma to the right side, we have here 1 over sigma to the right. Then substituting this mu for x in here, and then distributing it for each term in here, we have mu t minus mu over sigma, then plus mu over sigma. Then we can cancel out this minus mu over sigma and plus mu over sigma. Now for this one, we have a common denominator sigma. If we multiply the numerator and denominator of t by sigma, then we will have here sigma t minus 1 over sigma, or 1 over that is sigma over sigma t minus 1. Then we can cancel out this sigma and sigma. So what we're left with is negative 1 over 2 times sigma t minus 1 e raised to mu t, with the condition this one. Now let us combine our results. Now from here, our moment generating function is the sum of the results of evaluating each integral expression. For the first integral expression, we have this one, with the condition this one. And for the second integral expression, we have this one, with the condition this one. Then summing them up, this one is this one, and this one is this one. Then in here we have common terms e raised to mu t and 2. Then factoring this expression by these common terms, we have e raised to mu t over 2 in here, and then what we're left with is 1 over sigma t plus 1 minus 1 over sigma t minus 1. Then we have here a common denominator by multiplying the denominator in here and the denominator in here, which is sigma t plus 1 times sigma t minus 1. And then dividing this with this one, sigma t plus 1, we'll have sigma t minus 1, and then multiply by 1, we have sigma t minus 1. Then we have minus. Dividing this one by the sigma t minus 1, we have sigma t plus 1, and then multiplying it by 1, we have sigma t plus 1 in here. Then we have here sigma t minus sigma t, which is 0. Then we can cancel them out. Then we have here minus 1 minus 1, which is negative 2. So we have this one, negative 2. Then for this denominator, it is a sum and difference of two terms. So by algebra, it is square of sigma t minus square of 1, which is this one. Then we can cancel out this 2 in here and 2 in here. And then by multiplying both the numerator and denominator by negative 1, we can remove this negative sign in here. So we have here just e raised to mu t from here. Then for this one, we have 1 minus square of sigma t. Then we have our conditions, this one and this one, which are rewritten in here. Now combining these two conditions, we have negative 1 over sigma is less than t, and this t is less than 1 over sigma. So t is in between negative 1 over sigma and positive 1 over sigma. or we can rewrite it as the absolute value of t should be less than 1 over sigma. Then now we have our moment generating function, which is this one, with the condition this one, to make this one valid.